space. Okay, we have these 2 points, and now I'll draw a very mini three-dimensional Cartesian plane for us. Okay, just so we have an idea here. Point A. Okay, remember this is a rough sketch. Is at 7, -11, and 13. So some point way out here probably. That's point A. And it's also vector OA. Now, it's not the absolute value of vector OA because the absolute value of that is the magnitude. But we know that it starts at the origin, and then this would be our point A. Point B, on the other hand, is 4, -7, and 25. Say it's way up there. Okay. That's point B. Again, this is in 3 space, so it's very hard to see the way I've done it because it's technically 2-dimensional right now. Okay, and that would be OB. Again, not the magnitude, just the components of it. The very first question says find the magnitude of OA. Well, essentially what we need to do is we need to find we got to use Pythagorean's theorem to solve this. Now, this is a triangle that's on an angle. So it's technically on like an angle like this, and then the right angle somewhere like that. It's 3-dimensional, this triangle, in order to solve it. Now, normally what we do is a 2-dimensional triangle. Had I known what this vector is down here and this vector up here, I could just do this with 2 numbers. But we have 3 numbers here. And what this is saying is this length, however far it went across the x, can be solved with a right angle triangle to solve it. However high up it went on the z, we can use a right angle triangle to solve it. And however far it went on the y, we can use a right angle triangle to solve it. Okay? So, it gives us a formula, okay? And the formula looks like this. The absolute value, oh, that's of AB. Do we want AB? No, we want OP. Okay, of our position vector. So we're going to say OP in this case. Our position value's absolute value is equal to A squared plus B squared plus C squared. Okay? So there's a third term under here because we're in 3-dimensional space. And that is as long as this is A. Okay? We have our point A, which is x1, y1, z1. And let's say we had our point B, which is x2, y2, z2. So all that's saying is, in the position vector, if we want to know what the position vector is, so what that component is, so let's say that in this case, P is A, B, C. Okay. So what that's saying is we can just literally take the value of A, our position vector, plug it in, square it, position of B, square it, and then square root it to find the absolute value of going from the origin to that position. Okay? So for OA, that's really easy. We already have our values of A, our B, and our C. So we're going to find it for OA. And what happens here is the absolute value of, not OP, OA in this one, is equal to 7 squared plus -11 squared plus 13 squared, all square rooted. When we square root that all, it becomes 339, okay, which is roughly a little over 18, the magnitude of OA. That's how far it is. OB, same idea, because we have our values of A, B, and C. Okay? Well, OB, we're finding the absolute value of it, is the square root of 4 squared plus -7 squared plus 25 squared. When you add those all together, we get the root of 690, which is a little over 25, or 26, I think. So, a much larger value. I'm not going to put the decimals in because we're trying to keep it as exact values. Okay. So that gives us the magnitude of OA and OB. But the next question, it doesn't ask us for a magnitude, it's just asking us for the components or the position vector of AB. Because we know in 3 space, technically this is AB. But we want to know what that would look like coming from there. Or in other words, our OP. Okay, so what would this coordinates be? We're trying to find out what the 3 coordinates of this would be. What will A, B, and C be for vector AB? Well, in order to do that, it's a little different. When we're looking for AB, okay, what we're looking for is x2 minus x1, y2 minus y1, and z2 minus z1. So we're looking for the component values. X2 in this case is 4 minus 7. I know you can't see it, I apologize. And then negative 7 minus 11 minus negative 11. And finally, 25 minus 13. When we carry this all out, we will get negative 3 plus 4 and minus 12. Okay. So that's our components. We don't need to have the positive sign in there. Negative 3, 4, and 12 would be our position vector. If we were to move vector AB from where it is to starting at the origin, this is where it would point to. That's what it's telling us. And now that we have those values, the next question asks us for the absolute value of AB. Well, because we have the position vector, we didn't have the position vector, there'd be a lot more work to this. We'd actually take this thing here, we'd have to square each of them and then square root it, okay? So I'm going to show you what the formula would look like if we didn't have that position vector. And what it is we take the x2 minus x1, which gives us our A value, right? Remember, this gives us A, B, and C, which was our original formula above. And we square it, plus y2 minus y1, square it, plus z2 minus z1 squared. Okay. Now luckily we've already figured out what x2 minus x1 is. It's negative 3, so we're going to square it. It's all being square rooted. Plus we know what y2 minus y1 is. It's 4, so we square it. And z2 minus z1 is 12, so we square it. We square all those, ends up to the root of 169, which is a value of 13. Okay, I know I did the last calculations quickly. Well, what that's telling us is we can find the magnitudes of vectors if we start them at the origin very quickly without having to do this subtraction step in here, as long as we have the position vectors. This is, in other words, if we're going OA, OB, or OP. Okay?